My name is Tim Tumberg. I'm an archaeologist with the Minnesota Department of Transportation. I've worked for the state of Minnesota for more than 20 years. For about 17 years, I managed a cultural resource program with the Department of Natural Resources. Since January of 2018, I've been with the MnDOT Cultural Resources Unit. That's my primary employment, I guess. I also do a few small independent projects on the side under the auspices of 10,000 Lakes Archaeology, a company I founded with my wife about 25 years ago. I don't really actively seek out projects or solicit things, but I will respond to people who contact me because I'm on the Minnesota SHPO contractor list. And my primary research interest, I guess, is the iron mining industry of Minnesota. And a couple of years ago, I worked on a ore processing facility up on the Mesabi Range. And that's what I will be talking about today. My paper is titled Documenting the Gilbert Iron Ore Concentrator. In the fall of 1955, the W.S. Moore Mining Company, which is based in Duluth, announced plans to construct an iron ore concentrator near the Mariska mine pit, approximately 1 mile east of the city of Gilbert in Minnesota's Mesabi Iron Range. Prior to the Moore Company activity, the Mariska mine operated from 1907 to 1911 and again from 1920 to 1926, shipping a total of just under 366,000 tons during those 12 years. Reopening a mine after 30 years is a prime example of an ongoing mining industry process as advances in technology prompt continual adaptation. In 1939, professor of mineral dressing A.M. Gowden declared that the first few decades of the 20th century, quote, witnessed the introduction of unparalleled changes in the art of dressing ores and minerals, unquote. And I would suggest abundant evidence indicates that iron ore processing technology not only fit that model of unparalleled change, but it continued to expand and accelerate throughout the remainder of the 20th century. A major impetus for the 20th century technological shift in Minnesota's iron industry was based on the belief that high-grade direct ship ores would be depleted sooner than later. Direct shipping ore contained 50 to 70% iron and required little or no processing prior to shipping to the steel mills of Pittsburgh, Cleveland, and Chicago. Other ore types, such as taconite, though plentiful throughout much of the Mesabi Range, contained only 20 to 25% iron, and the lower grade ore needed to be crushed, separated, sifted, and rolled in an elaborate and expensive process of beneficiation. As early as January 1924, Edward W. Davis, known as the father of taconite, said that shipping grade ore constituted a finite resource that would keep the iron industry going at the present rate for about 20 years, but taconite would be viable for the next 500 or 600 years. Concern about natural ore depletion was valid, but by shortly after mid-century, optimism about the projected benefits offered by technological innovation was running high. The final line of a 1958 history of the Pickens Mather Company says, quote, in all directions, a prospect lies ahead and the horizon is bright, unquote. The eventual accolades for taconite include statements like, taconite revolutionized steel making and provided the iron ranges with a second wind. From an economic standpoint, taconite has been credited for keeping the iron range alive. Historic descriptions of iron ore types are wide-ranging. Edward Davis himself suggested, as this quote, which I'm not going to read, you can all read and presume, there's a nearly infinite variety of taconite forms. Some other authors focus specifically on the magnetic aspects of iron ore, but did not necessarily define taconite strictly according to its magnetism level. One of those quotes is, in the United States, premium quality blast furnace feed is being produced from the magnetic taconites of the eastern Mesabi Range. And other plants are carrying on further experimentation with the fine-grained magnetic taconite and non-magnetic taconites and semi-taconites of the western Mesabi Range. An environmental examination of the impacts of iron mining on the Mesabi Range identified 3 major and overlapping phases of iron mining in the Lake Superior District, from direct shipping ores, ranging from 1847 to the 1970s, to washable ores, 1910 to the 1980s, to taconite, 1947 to present, with washable ores being clearly differentiated from taconite. That explanation was, taconite, like washable ores, contained a low percentage of iron, but taconite ores required more intensive and extensive beneficiation technologies to return a profit. Unlike the washable ores that simply required mechanical removal of silica, taconite processing required more intensive steps such as fracturing the mineral deposit at the mine site, fine crushing and grinding of the ore at the beneficiation plant, magnetic concentration, and agglomeration, which is forming the fine ground taconite into uniform pellets. The Gilbert concentrator's operational lifespan of 1955 to 1963 would fit the period of significance for either washable ores or taconite, but if it is true that magnetic concentration is a necessary element of taconite processing, it would have to be assigned to the washable ore phase, because there is no indication of a magnetic separator on the 1961 W.S. Moore Company map. I want to give a shout out here to Julie Molina of Bar Engineering, who provided me with this map and saved me some valuable time on the project. The map labels the concentrator's main beneficiation specific features such as a water tank, spirals, hydroseparator, high density surge, crusher, scrubber, 8 jigs, and a jig surge. All of the machinery and equipment that had value and was reasonably portable is gone, and there is no readily apparent visible surface evidence of railroad tracks. Nonetheless, the preliminary site assessment found the site retained research potential because many concrete equipment foundations and bases, along with support infrastructure in the form of supports and abutments, remain extant on site and in their original locations, though in varied stages of disrepair. Show just a couple of the pictures here. The section of the jig bases. There's another view. Here's the base of the primary ore crusher. You can see the high ridge up behind it, and we'll get a closer view of that. This is taken from right on the ridge side of the crusher, and that right on top is where the truck ramp was, where the dump trucks would, or the ore trucks would pull up and dump the loads down into the crusher, taking considerable advantage of gravity to help them out there. But the most compelling feature on the site is the hydroseparator, which is a specific type of gravity concentration process known as heavy medium separation. Hydroseparators can be somewhat variable in form, but they employ essentially identical principles of separation. Essentially, it's a shallow tank, usually cylindrical, which is kept agitated by hydraulic water and or stirring devices. Pulp fed to the tank is separately discharged as a free settling fraction containing the coarser and heavier particles, and an overflowing fraction containing the finer, lighter material. The Gilbert concentrator hydroseparator originally comprised a 9-sided obelisk connected to a 3-sided square that forms the 10th wall on the west side. Maximum overall dimensions measure approximately 27 feet 6 inches east-west and 19 feet 8 inches north-south. Gilbert concentrator hydroseparator appears to generally fit the description of a door hydroseparator, which has been described as substantially an undersized door thickener. So you can see the convex bottom here, which is, or the concave bottom, which is different from the famous Cornish buttle that was excavated in the UP back in the mid-1990s. Perhaps as a means to provide access for the removal of reusable or otherwise valuable elements that comprise the original machinery, all of the north wall and the adjacent east part of the northwest wall of the obelisk had been removed. The missing wall portions, any historic preservationists here, cover your eyes and ears, serendipitously provided good backhoe access and dozer access so that the separator could be cleaned out mechanically. And I can vouch from personal experience, it would have been virtually impossible to clean it out by hand. That starting 3 or 4 years ago, I would still be working up there today trying to do that. It was a big matted mess. So this was looking very promising for documenting the base and the floor and everything, because when we got down here, we thought, well, okay, we'll just go away for a few weeks and wait for all the rest of the water and muck to dry out. We can come right back and get busy documenting it. When we came back to the site a few weeks later, this is what we found. So the matted mass that was in there is gone, but the water had filled right up. And this was the result of continuous seepage that we never were able to adequately address or rectify. We had a pump going, and that helped some, but it didn't really draw anything down completely. So it was stomping around in chest waders, and it didn't seem like there was too much of a chance that you would fall through anything in the bottom of a concrete floor, but used a big stick anyway. And another one of the dangers was the walls were not exactly in the most stable condition. But we were able to draw the water down far enough to expose the higher portions of the hydroseparator floor, and that enabled the following observations. The base and floor of the hydroseparator has a convex form that slopes down from the wall edges on the periphery toward the inside. The lowest point in the floor is approximately 18 to 24 inches below the edges and is not in or near the center of the generally circular shape, but offset to the northeast. The floor low point appears to funnel down into a drop spot that leads to an outlet tunnel of undetermined size that leads out from the northeast side of the hydroseparator to an undetermined location. The floor is made of poured concrete that is only roughly formed, and the observable area exposed by weed removal and water drawdown revealed no indication of scraping mechanisms, sweeping paddles, or a central shaft on which any such implements could be fastened. An inventory and analysis of historic mining sources concluded the Lake Superior Iron District historically was home to 103 beneficiation plants, with 88 of those being located on the Mesabi Range. Of those 88, only a handful remain visible, as the majority were removed for scrap decades ago. Although the number of extant sites functionally akin to the Gilbert Concentrator is unknown, most evidence suggests they are rare or constitute poor examples. Even if many beneficiation plants similar in size and scope to the Gilbert Concentrator remain extant in landscapes mostly unaltered since operations ceased, it's likely that the early mine buildings, beneficiation plants, head frames, and most other apparatus and equipment have been removed. Previously established guidelines for identifying and evaluating the significance of historic landscapes similarly note that a landscape that is the most significant, most intact, only remaining, earliest, best example, or a good example of the property type is more likely to be eligible than one that is altered, less significant, commonplace, or a poor example. Seems fairly self-evident. A preliminary evaluation of Site 21 SL 1245 concluded with the recommendation that the Gilbert Concentrator gains relevance and importance simply because no other sites of its type have been recorded previously. At this point, it is not clear whether the Gilbert Concentrator constitutes the most complete and representative, or even only, example of a specific site type, but it is relevant and important that no other examples of the site type have been previously recorded. Whatever category or phase it is assigned to is a necessary first step in the information gathering process, but it is more important that the Gilbert Concentrator constitutes the first Mesabi Range site of its type to be individually documented, especially because it can be reliably recording individual sites with precisely defined dates of operation enables larger scale comparative syntheses that enable meaningful interpretations of individual aspects of technological change, such as adaptation, diffusion, innovation, and independent invention. That's all I've got.